Good afternoon, everyone. Thank you for being here. Thank you, Professor Greco, for this presentation. Can you hear me? Okay, now I can hear myself. Okay. Thank you, everyone. Okay, so maybe we can start. First of all, let's see an outline of what I'm going to present. We will see something about the functional approach to quantum field theory, as Professor Greco introduced. Then I will briefly discuss the ON model and its symmetry. And then I will face the problem of solving the flow equations deriving from this ON model, both in LPA, which I don't have the time to present, but in this presentation I will talk about LPA prime, and in particular the two flow equations about effective potential and anomalous dimension. Then we see some plot about the effective potential, and then the main results, which are the critical exponents and the critical behavior of the system close to the second order phase transition. So let's start with a brief introduction about quantum field theory, how to approach it with a functional approach. The main ingredient of a quantum field theory is the generating functional Zj, which depends on the source J. And this is the main ingredient since you can functional derive all the endpoint functions from this functional via functional differentiation. So once you compute Z, you basically solve the theory. There is a more efficient way, let's say, to store information about quantum field theory, which is the generating function of connected correlators, which is this Wj, which is basically just the logarithm of Zj. And once you have this Wj, you can define via a Legendre transformation, you can just define this gamma, which is the effective action. And it can be seen like the generating function of one particularly irreducible vertices. Just to have a glimpse on what this phi is, if you take the functional derivative with respect to j of that expression, you end up with phi equal to the expectation value of the field in presence of the source j. So now one can compute gamma starting from its definition, but it's very difficult. So you have to find a way to compute it efficiently. And one way is to explode the functional renormalization group. To do so, you have to introduce an effective average action, which is this gamma k, which ranges between the bare action at the cutoff scale k equal to lambda to the effective action at k equals 0 in the infrared. And to do so, you have to define an infrared regulator functional via introducing this regulator term, which is this delta sk, which appears in equation 8, which is basically quadratic in the field and then contains a term which is probably called regulator, which is this rk. And once you have done this, you can introduce this effective flow equation, let's say. We can introduce the effective average action, which is this gamma k, via a Legendre transformation, which is modified via the regulator term. And once you have this, you do some computations, and you end up with equation 10, which is the main subject of the study, and is the flow equation, which determines how gamma k evolves through RG time, which is nothing but this ratio between k and the cutoff scale lambda. So when you have these, you can evolve through time this gamma k and obtain the infrared solution. Of course, you cannot solve it analytically, or you can almost always not solve it analytically, so you have to use approximation. And in this case, we will use derivative expansion, which means that gamma k is expanded in powers of the gradient, and in particular, we will stop at order, let's say, 1/2, and you'll understand soon why. First of all, let's talk about the theory. The theory is the ON model, which is basically a collection of n-scale fields with phi a, which goes from a goes from 1 to n, and of course, the bare action associated at the cutoff scale is the one given in equation 11. And in this case, we chose phi to the 4 potential, which gives a nice phase transition from the ON to ON minus 1, which is a spontaneous symmetry broken. And then this symmetry is restored via second order phase transition. And this is the one we are going to study. And of course, rho is the invariant of the theory, is just the scalar product of the fields. As I was saying, this is the approximation we are going to use, which is LPA prime. This is the expansion we have for gamma k, which contains the effective potential, which runs with scale k, so it depends on t. And then we have the derivative term with zk, which is the wave function renormalization factor which in this case should depend on the fields, but in this case is field independent, but time dependent. This is the lowest order approximation, which allows us to compute the anomalous dimension eta. And how do you get it? You define the running anomalous dimension, which is this eta k defined in 14, and then you just take the limit to the infrared of this eta k. So the limit k goes to 0. Now we face some computations, and the first thing to do to compute the effective potential is to choose a background field which is compatible with the ON symmetry of the model. And the easiest one you can choose is just the one which has the nth mode equal to sigma and the others equal to 0. So you end up with the 2-point function, which you need to plug into the flow equation, when you can distinguish the longitudinal and the transverse part of the 2-point function. Then the next ingredient is the regulator. And since we are in LPA prime, you need to put this zk in front of the regulator in order to preserve the scale invariance. And then the regulator we choose is the Littim regulator with this theta. And then alpha is a free parameter you can tune in order to obtain better results. Then you face all the computation and you end up with this flow equation 20. And in this flow equation, you can distinguish two terms which are shorthand notations, which are M1 and M2, which are nothing but the mass of the modes involved in the theory. M1 is related to the pions, the Goldstone modes, and M2 is related to the sigma radial mode. Now, what we want to do is to cast this equation into a diffusion advection equation. And to do so, we introduce a new variable, which is a conserved quantity, which is nothing but the sigma derivative of the potential. And of course, if you take twice the derivative, you end up with the u prime. And so redefine M1 and M2 in terms of these variable u and u prime. You can distinguish two contributions. One is the one related to the advection, so the advection flux, which is the one in 27, and which depends on the derivative of the potential, which in this case is u. And then the diffusion flux, which depends on the second derivative of the potential. So once you have done this, you can just take the whole derivative with respect to sigma of the equation for the effective potential, and equation 29 is what you end up with, which is nothing but an advection diffusion equation, which is the key ingredient of our further study. Now you have to derive, we missed the equation for zk, in particular for eta k, and to do so, we exploit the definition given in question 30, and then you, again, do the computation and end up with equation 31. And in the equation, we have the transverse and longitudinal propagators, which are nothing but the inverse of the 2-point function plus the regulator. Now, since we want to derive an equation for eta k, which is dimensionless, you have to define dimensionless quantities and rescale the equation 31. And to do so, we introduce the dimensionless field and the dimensionless potential, so rho tilde and v tilde. Once you've done this, you just transform in a dimensionless form the equation we had before, 30, and we end up with equation 34, which is dimensionless. And we have defined the threshold function MDT2, which is just a term which contains some integrals involving the regulator, the dimensionless regulator, which is defined above, and the dimensionless variable y, which is just the ratio of the two scales involved. And this is the equation you use to derive eta k. So now that we already have the flow equations, we can see some plots. This is the effective potential. And now I'm going to show you some plots at increasing time. The different curves differ from one another because of the choice of the ultraviolet minimum. So the red curve has the largest minimum, the purple curve has the lowest minimum. And as you can see from time evolution, what do we expect? We expect that the lower is the minimum, the more the system will end up in a symmetric phase with the minimum in 0. And bigger is the minimum in the ultraviolet, the more the theory will end up in a broken symmetry at the infrared scale. And this is exactly what happens. And we see the minimum is going back towards a smaller value of the field. And if the symmetry is still broken, because of convexity of the potential, we end up with a plateau in the broken phase. And this you can see also from this was the derivative of the potential. This is the effective potential. And you can see this also from the potential. You see it's going towards a plateau. OK, now let's switch to the critical behavior. First of all, we have to identify the order parameter of the phase transition. Of course, it is the minimum at the infrared, because if it's 0, we are in the symmetric phase. If it's not 0, we are in the broken phase. Now we have to find something which plays the role of the temperature. In this case, is the minimum at T equals 0, which means in the ultraviolet scale. Why? Because if you choose a value which is greater than the minimum, than a critical minimum, let's say, you end up in a broken phase. If you choose a value which is less than this critical value, which corresponds to C greater than TC, you end up in a symmetric phase. So with a minimum in the infrared, which is 0. Now we have to find basically this critical value. And to do so, you have to rely on the behavior of rescaled quantities. In particular, we will deal with rho tilde, which depends on k, and it's basically rho 0 divided by k. And we can see it from the plot how to derive the critical value or the scaling solution. First of all, you start with a definite value of the minimum, and you see if you go upward, you end up in a broken phase. Why? Because you end up in a finite minimum, and divided by k, this diverges as k goes to 0. If you choose a value which is less than the critical value, then you will reach the value of the minimum 0 at a finite value of k. This means that the curve goes downward. And in between these curves, you have the critical behavior. Of course, you will never hit with infinite precision this value, so you have to stay with these two approximations, the upper bound and the lower bound. Now we can finally switch to how to determine the critical exponents. First of all, we start with beta, which is the one which governs the order parameter. As we know, the order parameter has this power law behavior close to criticality, which is given by t minus t to the power of beta if we have t. In this case, we have rho 0 minus rho 0 critical to the power of beta. So you just end up with, you take the logarithm of both sides, and you end up with a line which has slope beta. And so this is how you derive beta. Now you see that the points are a bit, there are some points a bit off of the graph. This is for n equal 3 in the RPA prime. And I can justify this point because these do not belong to the critical behavior just because you have some error on the determination of the critical parameter rho 0 critical. So if you start to values which are too much close to this critical value, you end up with points which do not belong to the critical behavior. And that's exactly the opposite for the other points because they are too far from the critical behavior. So you expect them to be off of the line. And this is for beta. And this is also valid for the other exponent nu. For eta, there's a different approach. So nu, you basically start with a correlation length with diverges close to criticality, as we know, t minus tc to the power of minus nu. And in this case, rho 0 minus rho 0 critical to the power of minus nu. And you can relate this correlation length to the renormalized mass and compute the renormalized mass, which is basically the second derivative of the potential in the infrared limit. You can just relate these two quantities and again take the slope of this logarithm relation 41 and extract 2 nu as a slope. And this is exactly what I was telling. So you have the mass, you have rho 0 minus rho 0 critical. And again, you can see that these points are a bit off the line. And here the point starts to be off the line. And this is again for n equal 3 in the LPA prime. The last exponent we miss is eta. And in this case, you just refer to the behavior of the correlator, of the propagator close to criticality, which goes as a power law again. And you can extract the value of eta just looking at the behavior of eta k. Because as all the quantities, it reaches a scaling behavior, which means a k-independent behavior. And in principle, it should go with this critical behavior up to k equal to 0. But since we have a finite approximation for the critical value of the fields, we always end up with eta k, which reaches a plateau and then deviates from it upward if we are in the broken phase, or downward if we are in the symmetric phase. And this is exactly what you can do. So you extract eta from the plateau value, and then you see that you deviate upward if you are in the broken phase, and downward if you are in the symmetric phase. So now I show you some results obtained both in the LPA, which I didn't discuss, but it's basically the same approximation with z equal to 1. And we notice some details, let's say. The first thing we can notice is that the LPA prime values are always less than the LPA values. And this is understandable since in this case, eta is equal to 0. So somewhere this critical exponent has to be redistributed. And another thing we can notice is that these two approximations tends to coincide as n increases. And this is also understandable since for the large L limit, which means n to infinite, the LPA becomes exact. So eta goes to 0, and so you can solve the theory using only LPA. And another thing you can notice is that the errors you have on the points in LPA prime is greater than the error you have on the LPA. And this is because, of course, LPA prime involves more computation, so it's more difficult to go with a higher precision on the critical field, on the critical value of the field. Now we see, of course, eta, and eta is 0 in the LPA, as I said, and then you can see that nicely goes towards 0 in the LPA prime case as n increases. And this is the last plot for the critical exponents on themselves. That now I'll show you a comparison. Show you a comparison of these. I chose nu as a reference, and as a reference for the values of nu, I choose the one obtained in literature via conformal bootstrap, which is another non-perturbative technique, so that's why I chose that. And as you can see, I also compared these results with the one obtained in literature with the same technique I used, which means RG in the LPA prime approximation. And you see that the results of LPA prime, which are my results, are better, let's say, than the others using the same technique because we use a different numerical approach. And also LPA sometimes is even better. So now we can go to the conclusions. What we have done is to describe how to face quantum field theory using FRG approach and how to derive the flow equation. Then we apply this method to ON, and in particular, we derive the flow equation for eta k and for the effective potential in the LPA prime. Actually, I've done it also in the LPA, as I said. And then we have used this to compute the critical exponents in D equal 3 ON model for various n, and in both in LPA and LPA prime, and then compare these results with the one known in literature and obtain, let's say, an improvement with respect to the one with the same, obtaining the same framework. Thank you for the attention. Thank you
for your presentation. It's now time for discussion, which will be led by Professor Rischke from Goethe-Universität Frankfurt. Professor Rischke, unfortunately, has got a problem with his webcam, but will contribute with his voice. So, Professor Rischke, please.
Yeah, thank you very much. And thank you, Fabrizio, for the nice talk. I would like to ask a few questions. It seems that you have studied the critical behavior for this ON model in 3 dimensions. Yes. But of course, in principle, you would think that you would have to do this in 4 dimensions at some finite temperature. So what justifies the use of 3 dimensions?
Yes. This is justified by the so-called reductional dimensional theorem, which in this case, what does it mean? It means that you can study a d-dimensional theory with at finite t using a d-1 theory at t equal, in this case, is t equal infinity, let's say. And why you can do this? Because you are close to phase transitions. And because of close to phase transitions, the length scales involved are so big that let's say the t dimension, the t finite dimension does not contribute, so you can neglect it. Mm-hmm. And this, from a practical point of view, this means that if you look at the free energy of the system, these are some contribution given by the Matsubara sum. So you have the different modes which contributes, but since you are interested close to phase transition, you are interested in the divergence, or divergence, let's say, singular part of the free energy. only the zero mode of the Matsubara sum gives such a contribution. The other one are regular. So you just take the zero mode and you can neglect the other ones.
Yeah, very good. So it's basically the universality close to second order phase transitions, which you utilize here.
Yes.
Very good. And then it's very interesting your comparison with other results. So what precisely makes your method better than what people have used previously? Can you elaborate a little bit on this?
Yeah, maybe I can discuss a bit about the method I use. If you want, yeah, I think I have some backup slides somewhere. I have to go. Yes, spoiler. Okay.
Ah, yeah. Okay.
Yeah. Okay. This is basically central. Yeah, I will use a finite volume scheme, and this is done because in this way you can treat also discontinuities. So if you face hydrodynamic equations like the one you can cast into the flow equation, it's always a good way to treat it using physical meaningful schemes, which means that can treat, for example, discontinuities. If you use finite differences method, you cannot handle them. So basically what I do is use this Kurganov and Tadmor scheme, which has just as a main ingredient you just compute the speed velocity of the characteristics, which is the